Okay, so let's continue our exciting journey. I hope you found it exciting. I'm not 100% certain, but that's my belief. So what I did here is to understand whether we can certainly use, it will make our life significantly simpler if we can use the same formulas for the coordinate functions in nonlinear analyses that we used in linear analyses, and to what extent it will actually will result in the same data. So what we did is simply supported PCB, first linear, nonlinear, then also elongated, then clamped at the end PCB, linear and nonlinear. Again, it's clear that the difference is in simply supported, the boundary conditions are that the displacements, vertical, lateral displacements at the supports are 0, and the bending moments, that means in terms of displacements, the second derivative is 0. While for the clamped board, there also displacements are 0, but it's angles of rotation that are 0, not the bending moment. So the first derivative with respect to the x of the deflection function should be 0 at the supports. And that's the difference between a simply supported board and a clamped board. But let's start first with the simply supported. So for the simply supported board, we have here a coordinate function. Then we know we did it many times. We calculated the linear frequency. Then we calculated the initial velocity with consideration of the effect of the mode. And the linear amplitude was 6.9, approximately 7 millimeters. Parameter of nonlinearity was huge. Then dimensional parameter was 132. So reduction factor was 0.34. So in other words, the linear amplitude is only about 1/3 of the nonlinear amplitude is only about 1/3 of the linear amplitude. So the nonlinear amplitude is 2.37. Parameter of the nonlinear frequency, we did it several times, is whatever we got, 3097. Modulus of the elliptic function, we calculated. Let me tell you this, for linear vibration, this modulus would be 0, right? Because in this case, the parameter of the nonlinear amplitude, sigma, and the nonlinear parameter of nonlinear frequency, sigma, and the nonlinear frequency itself, p, and the omega would be equal. In this case, k would be 0. So the deviation of the k value from 0 is indication, an indirect indication of the level of nonlinearity. The elliptic integral, in the case of linear vibrations, would be pi divided by 2, which is 1/6 something, and here's 1/8 something. Nonlinear frequency, 2066 1. So you see it's a little bit lower than parameter of nonlinear frequency. Maximum acceleration is huge. 2320, maximum curvature is also calculated. Now, with a clamped PCB, we consider two cases. When with approximate coordinate function, in this case is cosine squared pi x divided by 2a. And by using this approximate coordinate function, we certainly satisfy the boundary conditions at the end. When x is equal to a, the x is 0, so deflections are 0. And if you will take the first derivative of x, you will have something which is proportional to sine pi x divided by a. And in this case also, if x is equal to a, it's 0. So this approximate coordinate function satisfies the boundary conditions for the clamped board. And it's well known that this approximate function is quite often used when you want to obtain the approximate value for the linear frequency, because the linear frequency is not very much sensitive to the actual shape of the approximate function, provided that you meet, of course, the boundary conditions. And you go through all these routines that we already went through, and the reduction factor here for nonlinear amplitudes is 0.74. So then we calculate all these, and whatever number we got, I simply showed them, because we will compare all these results in one table later on. The calculations of nonlinear amplitude are carried out in table 2, and as evident from this table, so the nonlinear amplitude is 1.9, and there are certain parameters that are important to consider. And the mu is a nonlinear parameter of nonlinearity, and linear amplitude is 2.6, and nonlinear is just 1.9. The difference is not that dramatic. So the obtained value of the nonlinear amplitude is substantially larger, about 20%, than the amplitude obtained using the approximate expression of the coordinate function, phi. But this is a very important table, and I will elaborate on that. So what we did is, first we assumed a certain function, and we knew in advance that if the amplitude changes from 0 to infinity, this function changes from infinity to 0. And then we simply assumed different amplitudes, and we went through the entire routine, and we assumed amplitudes because we needed the amplitudes in order to calculate this function, the stresses, and that and this. And then we went through the entire routine and obtained amplitudes based on these parameters. And it's clear this approach is quite often used in engineering and applied science. If we assumed amplitudes, you see here in blue, 2.0267, or 1.808, and we ended up also with amplitudes which are close to that. And based on this, by interpolation, we determined actually the actual amplitudes and everything else for this particular example. And we calculated the parameter of the linear stress, and all the parameters of the nonlinear stress, and everything what we needed to, we went through the same routine. Now I want to elaborate to discuss in detail this final table. What you see in this table, for the printed circuit board, in the first column, there are different parameters of vibrations. Then for a simply supported board, you see the numbers. We will discuss them. For a clamped board, first for the approximate coordinate function, where the cosine squared pi x divided by 2a, and then I calculated also the coordinate function, the actual coordinate function, that I simply didn't presumed it. Whatever we got. So in here, take a look at the difference. In linear frequency, yeah, substantial difference. In initial velocity, also you see a difference between simply supported. And let's now just compare two columns. You'll see the column in the middle. But the most important two columns, there was simply supported board and the clamped. In both cases, calculated coordinate functions. For the simply supported, we came to a conclusion that the basic equation, the governing equation is fulfilled even if you'll assume for the simply supported nonlinear vibrations also the same coordinate function. It's fine. It's not fine in the case of clamped function. And you see there's a significant difference between the presumed coordinate function and calculated function, and also there's a significant difference between the linear supported and clamped, of course. And you see here that the maximum acceleration is even in simply supported is it's 2,500 approximately G's, while for clamped is 1,066.47. So all these parameters are here for, oops. And I made this, I used just a portion of the table that is published, but I want to simply indicate to you here that you can calculate all these parameters for the simply supported and decide whether you can assume the approximate coordinate function and whether the clamped coordinate function calculated based on the calculation is substantially different of this presumed function. And indeed, it is. And therefore, the conclusions are that for the simply supported, you can get away with nonlinear analysis by using the same coordinate function that you used for linear analysis, while for nonlinear, while for the clamped board, you cannot use the same function that you used for linear analysis, but B, you also cannot use the function in which quite often you can get away in linear analyses, which is cosine squared pi x divided by 2a. So the summary of this analysis is this: a simple, easy to use, and physically meaningful analytical mathematical model has been developed for the evaluation of the effect of the coordinate function on the dynamic response characteristics of an elongated printed circuit board to the shock load applied to its short edges as a result of a drop impact. So we considered here again a situation when I have an elongated printed circuit board which is supported only at the short ends, and it's not supported at all along the long ends. So it's in effect it's an elongated beam like a strip. But in the first case, we assumed that the short edges of this beam were simply supported, and in the second case, they were clamped. The shape of the coordinate function for a simply supported PCB is not affected by the in-plane membrane forces, and therefore can be considered the same in linear and nonlinear analysis. Only the span, PCB length, and the amplitude of vibrations affect this shape. The coordinate function in the case of a clamped PCB is affected by the in-plane membrane forces, and the practical calculation procedure is developed for the evaluation of this function and its effect on the vibration characteristics. The numerical example carried out for a particular printed circuit board has indicated that the majority of response characteristics, linear and nonlinear frequencies, initial effective velocity, linear and nonlinear amplitudes, accelerations, decelerations, maximum stresses are strongly affected by the response function, and therefore in practical applications, this function should be evaluated based on the developed predictive model. The other problem associated with nonlinear vibrations that I already mentioned to you has to do with whether you can substitute a shock load of final duration with a instantaneous impulse, and we came to the conclusion that you always can do that in the linear system if the duration of loading doesn't exceed 1/8 of the period of vibrations. But even if the duration of loading is as significant as 1/4 of the period of vibrations, even in this case, the error is not very much. It's still about 5, maybe 6%, while in the case when it's only 1/8 of the duration of the period of vibrations in linear system, the error is absolutely minimal, just a couple of percent. But how does it work? Or does it work in the case of a nonlinear system of the type in question, when we have membrane forces? So I call it Duffing oscillator because that's the type of a linear or nonlinear system that we deal with. It's a single degree of freedom system with a rigid cubic characteristic of the restoring force. And so the Duffing oscillator subjected to an instantaneous impulsive load or to a constant suddenly applied load of finite duration is a suitable analytical mathematical model that can be used to evaluate the physical behavior of a printed circuit board subjected to drop or shock tests. We have already done that because we derived this equation and it turned out to be of the Duffing type. When modeling the dynamic response of a printed circuit board or a surface-mounted device package, including a ball grid array structure on the board level, to an impact load applied to the PCB supports during drop or shock tests, there is an obvious incentive in trying to simplify the analysis by substituting the impact load of finite duration with an instantaneous impulse. On the other hand, when there is an intent to replace drop tests with shock tests, one has to properly tune the shock tester in terms of the magnitude, duration, and time dependence of the applied load so that to adequately mimic the drop test conditions and to obtain physically meaningful experimental data. That goes without saying. So the analysis is performed for the elongated printed circuit board employed in an accelerated test vehicle, which is experimental setup, and the short edges of the printed circuit board are simply supported while its long edges are free. In the in-plane, so it's the same printed circuit board type that we used to analyze whether it's possible to stick with the same coordinate function in nonlinear analysis that we used in linear analysis. So here we use the same model, I mean in terms of the same structure, to answer this question about whether a short-term load of finite duration could be substituted by an instantaneous impulses. So our ultimate goal is to eventually use obtained experimental and modeling information for the prediction of the physical behavior and performance of the printed circuit board itself, the surface-mounted package, and especially the ball grid array solder joint interconnections. And here are the results. I'll simply describe for you the results, although then I'll show a little bit of numerical examples, because the procedure is pretty complicated and cumbersome, although correct and useful and insightful. We showed that the practical problem of interest is highly nonlinear, even for very low, as low as I would say here, in 10 millimeters drop heights. So in other words, for even very, very low drop heights, I said a couple of hours ago that probably about less than an inch, but here is even less than a half of an inch. We obtain exact solutions in elliptic functions to the Duffield equation for the cases of an instantaneous impulse loading and a suddenly applied constant force. We use these solutions to determine the error in terms of the predicted amplitudes and accelerations from substituting a constant load of finite duration with an instantaneous impulse. We show that the nonlinear oscillator, now you'll see a couple of examples, that the nonlinear oscillator in question is less sensitive to the duration of the applied load than the linear oscillators, and that its sensitivity decreases with an increase in the degree of nonlinearity. I want to elaborate a little bit on that and to explain the physics, why it happens, why it's not something that couldn't be expected, but just the opposite, something that could be expected. You remember at the very beginning of our course, I said, why should we treat some systems, why we treat some systems as static systems and others as dynamic systems. And the difference is this: if we have a system with a very, very high frequency of natural free vibrations, then even a load which is not that durable with respect to this system is a static load. So in other words, if the system vibrates very, very, very rapidly, the load, almost any load, should be considered as a static load. On the other hand, we have just discussed for several hours that nonlinearity results in a significant increase in frequency. So the same load that was or might have been dynamic for a linear system might be static for a nonlinear system. And if it's a static load, a change in this duration, it's static anyway. That's no wonder. That's the physics of what happens. Exactly because the nonlinearity results in significant increase in the natural frequencies, it stiffens the system and makes it sort of more, it's not that linear, but more resistance, actually more resistant or less sensitive to the change in the duration of loading. And therefore, since a linear system, in a linear system, the vibration period is a characteristic of the system itself. And in a nonlinear system, it depends strongly on the level of the applied load as well. And nonlinear analysis for a particular load level, drop height, should be carried out before an assessment of the error from the substitution of one type of loading with another one is decided upon. So this is mandatory. We cannot just shoot from the hip. We have to calculate to do these nonlinear analyses. But after that, we shouldn't be surprised that we don't have to impose such a stringent requirements for the duration of loading with respect to the natural period of vibrations of the system as it is in a linear system. At the same time, if it's only slightly nonlinear system, but look, our system, actual real systems, are not slightly nonlinear. They are very strongly nonlinear. Look, even 10 millimeters, 15 millimeters drop height with next to nothing results in significant nonlinearity. Therefore, that's sort of the good news that in these types of system, we can get away in many cases, and I'll show you now a table with all the static analysis, so the dynamic response is not that important. On the other hand, not in these particular cases, but in other cases, when we have slightly nonlinear systems, where the frequencies of these systems are still significantly higher than in a linear system, that means that the periods are significantly smaller. That means that the requirement that the duration of the load should not exceed 1/8 or maybe 1/4 of the period, these requirements in a slightly nonlinear system will lead to significantly shorter acceptable durations of the load that can be substituted by instantaneous impulse. So the bottom line, there's a significant difference between slightly nonlinear systems and highly nonlinear systems. If it's a highly nonlinear, it makes our life good again. We don't have to care. We can get away with a static approach. And we have to do that at the same time for nonlinear systems which are just a little bit nonlinear, but again, this a little bit can mean a lot. That means that it imposes very stringent requirement about how short the duration of a load of finite duration should be, so that it could be indeed substituted by a instantaneous impulse. We show, where are we? In the case of a suddenly applied and suddenly removed constant loading, the substitution of an impact load of finite duration with an instantaneous impulse is possible if this duration does exceed 1/8 of the period of vibration corresponding to the parameter of nonlinear frequency. And this parameter is somewhat greater than nonlinear frequency itself. But this is pretty much the same rule of thumb that should be used in linear systems. Systems with a very high degree of nonlinearity, with very large induced membrane stresses, behave like quasi-static systems with an extremely high natural frequency. And in such an extreme case, their response becomes independent on the duration of the load. Not after this result was obtained, we can understand its physics, but prior to that, it wasn't obvious, but at the same time, we still have to answer the question how nonlinear is really strongly nonlinear and how nonlinear is not strongly nonlinear. Preliminary modeling is imperative to decide on the right model that should be used to adequately interpret the test data. And take a look at this table. And here you have different parameters of nonlinearity. Let's start with this one. Let's say this k sub q with 0, which is the factor of the elliptic function. Or let's view the delta, which is a characteristic of nonlinearity. And for linear systems, it's 1. For highly nonlinear systems, it's square root of 3. So it doesn't change in very large, significant range. But also take a look. When it's 1, you have here pretty much the same data results that we obtained for linear systems. But at the same time, if we will go in horizontal direction, and we want to see how the degree of nonlinearity affects these factors, we will be pleasantly surprised that the significant increase in the degree of nonlinearity, highly nonlinear system, still enables one to use a load of finite duration, and we should be treated as a static loading, because again, if the natural frequency, because of the level of this loading, is very high, this loading is static. And here the numerical example was carried out for a printed circuit board with its dimension is 2A, thickness is 1 millimeter, so the board that we already used. And here you can see we calculated the data for the situation when the board is dropped from different heights. We start with 10 millimeters, 50 millimeters, 500 millimeters, and 900 millimeters, which is 900 the standard. But even long before we reach this 900, the standard, we see that the the nonlinearity has a significant effect on the results. For instance, the linear amplitudes increases, of course, dramatically, but the nonlinear amplitude increases a little bit, certainly with by a factor of 4. Here you see the maximum acceleration. Certainly, yes, it's significantly higher. There should be in highly nonlinear systems. It's 2,300, while with a small degree of nonlinearity, it's only 71. So it's the same. You remember we discussed by a factor of 3, and that's the factor of 3 certainly manifests itself. Slightly nonlinear, almost linear, 71, and highly nonlinear, although a different approach was used here, was 2,320. Also, the k value, capital, let's take small k. For a linear system, the small k sub z is simply 0, and then it increases with an increase in nonlinearity. But again, there's not dramatic increase between small nonlinearity like 10 and like 900. Look, if we'll go from 10 millimeters to maybe 1 millimeter, which is next to nothing, in this case we'll get probably k would be equal to 0. And here's calculations also of other parameters and depending on the drop height. As you see the drop height, which characterizes the degree of nonlinearity, you see the drop height changes at a dramatic factor of almost 190. And the accelerations, yes, here displacements, they change significantly, but not that dramatically. So the conclusions for this part is the Dufing oscillator, that's a single degree of freedom system with a rigid cubic characteristic of the restoring force, is a suitable analytical model to analyze a nonlinear dynamic response of a printed circuit board subjected to drop or shock tests. Simple and physically meaningful solutions were obtained for the above oscillator when the excitation force can be idealized as an instantaneous impulse or a constant suddenly applied load of finite duration. The obtained solutions and the calculation procedures can be used to model the dynamic response of a printed circuit board or a particular surface-mounted device package, including ball grid array systems, on a board level to an impact load applied to the printed circuit board to supports during drop or shock tests. The above solutions can be used particularly to assess the error from substituting in a modeling effort an impact load of finite duration with an instantaneous impulse. They can be used also when there is an intent to substitute the drop tests with shock tests and to properly tune the shock tester so that the drop tests conditions are adequately mimicked and physically meaningful experimental data are obtained. My paper on that subject that was published about 10 years ago, whenever, addressed only linear systems, and this is a new result concerning nonlinear systems. Although the analysis is carried out for a simplified case of a simply supported elongated printed circuit board employed in a specific accelerated test vehicle whose ultimate goal is to predict the physical behavior of a surface-mount device, and especially the performance of a ball grid array solder interconnection, it can be easily generalized for a printed circuit board with other boundary conditions and with a finite aspect ratio. Of course, when we will run another experiment, it can be, should be, but it's a straightforward way to modify this, these formulas. But the general procedure will be the same, and the result will certainly be similar. The case of a linear oscillator, very small printed circuit board deflections, is also considered, and we show that nonlinear system with a rigid characteristic of nonlinearity is less sensitive to the duration of the applied load than a linear oscillator, and that this sensitivity reduces with the increase in the degree of nonlinearity. While in a linear system the period of vibrations is a characteristic of a system itself, in a nonlinear system it depends strongly on the level of the applied load. For this reason, a nonlinear analysis for a particular load level, drop height, should be carried out before an assessment of the error from the substitution one type loading with another is made. And our analysis has indicated that even very low drop heights, as low as just 10 millimeters, resulted for actual highly flexible printed circuit board in appreciable in-plane membrane forces, thereby making the printed circuit board dynamic response nonlinear. This means that the ability to predict the physical behavior of a printed circuit board in actual conditions is absolutely crucial. This could be done on the basis of the solutions and calculations procedure developed here. Again, for other situations, these solutions should be slightly modified, but the principle will not change. And the developed analytical dynamic models clearly indicate the role of the major. This is a summary for a nonlinear part of my tutorial. The developed analytical dynamic models clearly indicate the role of the major parameters that affect the dynamic response of a bare printed circuit board and a printed circuit board with concentrated masses to the shock or drop impact applied to the PCB support contour. The calculated data based on the above analytical models are in good agreement, as we saw with finite element calculations. Thus, the models can be successfully employed for the analysis of the dynamics of the ball grid array response on the board level and can be used with confidence when analyzing the experimental data and to developing if necessary new, more adequate experimental setups that lend themselves better to easy interpretation and long-term reliability predictions. Now I will talk, and that will be the last part of my tutorial. I will talk about shock protection of portable electronics. And it's only a peak of an iceberg, because still a long way to go for many of us, many of you, to understand and to ensure the reliability and the ability of portable devices to withstand dynamic loading. But the existing devices, although we don't understand everything and we don't understand many things, they are reasonably reliable. The most important thing, if your device, you drop it and it fails, it's not the same as a shipwreck, and not the same as a accident with an aircraft or a collapse of a bridge. So it's not good, but it is a consumer product. So in many cases, by the way, its quality due primarily to how convenient it is, how nice it looks, how that and this, rather than to its reliability, but reliability is certainly also important. It's always, since I mentioned the word reliability, in general, we should have in mind that we always, as far as consumer products are concerned, we want to come up with the best possible compromise between the reliability, time to market, and cost. So we should think that although reliability costs money, but first of all, understanding is important. And if we understand what happens, we can make things very cost-effective and at the same time reliable, and we can reduce dramatically the time to market. So I will talk in that section, final section, or final, because it will be also one small section about photonics. Shock protection of portable electronics. First, I'll examine a 2-degree of freedom system, and it will be NCR design, National Cash Register design, that we dealt with about probably 10 years ago, but it's not something that has become obsolete, because the results are very interesting, and they certainly can be used in portable electronics, which they are not used yet. And maybe there is a reason for that. We don't want to make the structure overcomplicated, even pursuing a good thing of increasing reliability. So then I will consider conservative buffering oscillator with application to shock protection of portable electronics, and ideal shock absorber, ideally what we probably should be shooting for. And then nanowire array is a suitable cushion for shock protection of a portable device. Here's the shock protection of portable electronics in National Cash Register design. Here I want to describe for you this. What you see here, actually, what we tried to protect is the plate element. You see it in the middle. It's a piece of glass, very vulnerable. So the structure that NCR, a little bit with our participation, that primarily NCR has come up with for some of their devices, is this. They put this plate element into a, what they called it, a gasket. And the gasket was a rubber material, rubbery and at the same time material with significant dissipation. Then the entire thing, that gasket was put inside of a metal structure that they called, we will call it a chassis. And this chassis also, a flexible grommet was employed, which is a different name, but in effect it's also like a played the role of a gasket. That's something, a compliant element. Flexible grommet. And all this was put inside of a cabinet. And this cabinet was a enclosure. So actually what you see, I will call it a box in a box, because the plate element, the vulnerable element, is put inside of a gasket by using a certain compliant structure, material. Then this subsystem or assembly, also by using a flexible grommet, was put inside of a cabinet. And then we modeled that with a model that you see on your right-hand side, which is this plate element, has a first row of flexible elements with the spring constant of K sub 0. K sub 0 that corresponds to the gasket. Then you have M sub 0 is actually the plate element that is supposed to be protected. M sub 1 is the mass of the chassis. And then K sub 1 is the spring constant of the flexible grommet. And the cabinet, of course, has a tremendous mass, but we simply assumed in our analysis the very moment when it hits the floor, it sticks to the floor. So it will not bounce back, although in reality it might not be the case. And when sometime maybe we should consider that it might not be the exact situation. But in this analysis, and it was published in IEEE at that time, it was not even CPMG transactions, it was CHMT, Components, Hybrids, and Manufacturing Technology, was published in 1994. And this was the analysis, and let me show the results. This is one of the results. And what you see here is the response of this structure. The first view graph, the first plot on the left, figure 1, has to do with displacements, and the plot on your right has to do with accelerations. And we have already discussed, generally speaking, you want to kill two birds with one stone. You want to have low displacements and low accelerations. It doesn't happen this way. Therefore, in the real design, we want to end up with the best compromise, but we want to understand how these two governing parameters behave. And what you see here, these curves were obtained, it's a function of time, how these processes develop. And you can see if the ratio of and this is a system, generally speaking, has 2 degrees of freedom. And if it has 2 degrees of freedom, it has 2 frequencies. And these 2 frequencies here in this notation are gamma 0 and gamma 1. And the ratio of 2 frequencies, if it's close to 1, we have resonant conditions. And certainly, what we certainly want to avoid, we want to avoid a rigid impact. So we want to avoid a situation when the vulnerable element goes down, and because the vulnerable element goes down, and because of the resonant conditions, and you know the resonant conditions, they result in the fact that between the excitation force and the triggered vibrations, the difference in phase is 90 degrees. So because of that, we simply don't want to have a situation when this vulnerable element will go down, and the cabinet will stick to that, and the chassis will go back, and we will end up with something like that. That's certainly the worst thing to have. And this corresponds to the resonant conditions between 2 frequencies. So if these 2 frequencies are close to each other, that's certainly the situation that we want to avoid. And what you see here, that if it's 0.9, the displacements become huge, the amplitudes here on the right become huge, the dimensionless displacements and amplitudes. At the same time, if you have this frequency ratio is only 0.5, you're in good shape, so the vibrations do not increase, do not accelerate. So this analysis actually indicates how you can play, what you can possibly do for the given masses. You can certainly change some masses. You cannot change probably the mass of the glass inside, but you can change the mass of the chassis. You can change also